Number 2 for waves is about wave interactions. The learning intentions are the same as the previous one. I'm just reminding you to make sure that you read the text sections, watch the Rollo videos, and take Cornell notes from this presentation. So when a wave changes medium, some energy is reflected, some is absorbed, and some is transmitted. So we'll quickly do reflection, and we're going to see all of this in pracs. So don't be too panicked about it if it's stuff that seems really unfamiliar. When something bounces off a solid barrier, and when we draw our waves, we often draw them this way with the odd shape because it gives us an idea of where the front and the back is when it reflects. So when something bounces off a barrier, it always bounces back on the opposite side. When we have a pulse that goes from a slow spring or a slow medium to a fast medium, when it reflects, it does some strange things. And I should have actually drawn a second set for each of these ahead of time. I'll quickly do that now. So, when we reflect off a fast barrier, we almost try to get our relative speeds in part of the diagram as well. The transmitted pulse is always on the same side, but in this case, the reflected pulse is also on the same side. When we go from a fast to a slow, obviously the transmitted is always on the same side, and we try to represent the relative speeds, but the reflected is on the opposite side. These are things we have to not remember. These are things that have to go in your notes so that there's no chance of forgetting at the important times. I think you did a little bit about wave fronts last year and reflection and stuff like that. When a wave front bounces off a barrier, so here's the wave front, and always looks complicated when you do it this way, but if you in fact just take the direction, so if the red is the wave front, so an actual straight wave, the green arrow is the direction that it goes. If you just continue the arrow and bring it off at an equal direction, then you can always get the reflected because it's at right angles to the direction. And we know that if we then got more technical, theta 1 and theta 2 are equal. Because angle of incidence equals the angle of reflection. A strange concept, and I'm not sure you've heard about in the past, is a thing called superposition. Superposition is really not complicated. It really is just the addition of wave amplitudes. So we'll do an extreme example. We'll only draw 2 positions because I just want you to get the idea of a square wave and a triangle wave, and when they meet, it's always a good idea to draw the separate waves and then just draw the overall as well. And then you'll find that if you try drawing the overall, you get to about there, and we actually just have to add the shapes. So superposition just means adding the shapes. And also, obviously, adding the shapes in the opposite direction if there are opposite sides of the opposite sides of the spring, or the string, or whatever we're sending to waving. Last concept for this one, and this is a strange thing to start getting your head around, is a thing called resonance. But we will experience it in class. So a resonant frequency is one that matches the natural properties of an object. Example, and we'll do this in class on Friday. So what I want you to make sure you watch, and I'll upload them, some videos. Wine Glass and Tacoma Narrows Bridge. But we'll also do other resonance stuff in class. Now, one thing to think about is that when resonance occurs, the amplitude is larger than the applied amplitude. So you get really exaggerated effects when you've got resonance. And that's because the waves just magically add together. It feels like magic when you first see it. They add together because they're bouncing off the end and coming back and reinforcing each other, so you get a really big increase in amplitude, and we'll see that in class. Okay, that's the end of this one.